2 of the Axis conference, and we're starting off with a session about celebrating, how we got here, the legacy of the flagship missions that have characterized most of our careers, I think, the Chandra and XMM. Mike will be chairing the session, and Mike.
Great. So we're first going to hear from Pat Slane about the wonderful 25 years with Chandra.
Okay, great. Thanks. Is the mic on? Yeah, the mic is on. Okay. Great. Thanks, everyone, for showing up this morning. Thanks for the invitation to come down and talk about this. It's an exciting place to be giving this presentation. So I'm going to start very quickly here with with not advancing the slides. How's that working out? I hear the click sound. That's better.
Yes, but it isn't spinning.
It's not spinning. No, it's fine. It's fine. So far, so good. Okay, so I'm going to start things out here with an image that a colleague of mine, Thomas Connor, gave me. It's something I'm sure you all recognize. This is the X-ray sky from the ground. It represents what we knew about the X-ray sky when I was in grade school. So don't think too hard about that. We've obviously come a long way. It's a really great history story. I'm not going to give it to you. It's a great thing to talk about over beers. But I will say that if you think about what happened. So first of all, obviously, we have to do X-ray astronomy from space, and that wasn't possible until the space age came along. When you think about what was initially done, which is shown here in this paper from 1962 by Giacconi et al., where they launched the sounding rocket and looked for fluorescing X-rays from the moon, which they see as a little blip in the plot that you can see there, but also discovered this whopping signal in the direction of Scorpius, which later was recognized to be the creating neutron star system Scorpius X1, as well as a non-zero flux of X-rays all the way across the sky. Okay, so from that point on, leap forward many years to where we are now, and we have the Chandra X-ray Observatory. The observatory, as everybody here knows, so I think I can go quickly over this, is characterized by high-resolution mirrors. That's the stimulus, of course, for Axis, and so we all know why high angular resolution is important, though I will show you many examples that demonstrate that. The observatory, as again, I think most of you know, is equipped with 2 cameras, a high resolution imager, microchannel plate device, a CCD that offers high resolution imaging, as well as medium energy resolution, so you can do spatially resolved spectroscopy, a grating that can be swung into the beam to give you a dispersed spectrum that produces optical quality spectra of X-ray sources. And the core of Chandra that makes it unique is the quality of its mirrors. The angular resolution of the mirrors has a half energy width at 1.5 kilovolts of about 0.5 arc seconds, 90% encircled energy, just under an arc second at that energy. And with the background that is in the detector, that means that within one of those resolution elements in a million-second observation, you would expect to get about 2 random background counts. So as a result, when you do a modest observation with Chandra, if you do 100 kilosecond observation, which isn't even so modest, and you detect 5 sources, 5 photons, you've detected a highly significant source. And so this produces a capability to do very amazing things with the telescope. First of all, that haze that I was talking about, that low level of X-ray flux that was recognized in the earliest detection of non-solar X-ray sources in the sky, is resolved into many different point sources. Over 90% of that haze is resolved into point sources. Those point sources can be characterized by their type. This plot here shows the distribution. The green is a flux distribution for stars. The blue is for galaxies, and the red is for AGN. And so what you can see is that that diffuse X-ray background is predominantly supermassive black holes. The highest density from this deep observation, this 7 megasecond observation with Chandra, the highest source density corresponds to about 25,000 supermassive black holes per square degree. Okay, I'm going to take us from that high resolution resolving of the diffuse X-ray background through a range of astronomy topics that Chandra has made contributions to, obviously very much skimming the surface. But on stellar life cycles, and of course, I study supernova remnants and pulsar wind nebulae, so forgive me if there's a little bias in some of this. But one of the outstanding and early observations of the Crab Nebula, where we always knew that there was a very rapidly spinning, highly magnetic neutron star generating pulses that one could observe in the radio and such. This observation shows where that neutron star is. It shows a little ring around it with an underluminous zone inside the ring where the cold wind is expanding from the pulsar's magnetosphere out to where it joins the nebula in a shock, because it has to slow down to join the flow of the nebula. And that termination shock is recognized from models of how this all works as being in the equator of the system. So this image shows us where the equator of this pulsar that far away is actually residing. The jets are known to come out in the polar directions. So we see these jets, these equatorial rings, and then a larger equatorial torus that defines the entire geometry of the Crab Nebula system and shows how the spin down energy is being converted into relativistic outflows. Another early observation, an earlier observation, in fact, this is the first one that was released to the public, is of Cassiopeia A. Cassiopeia A is a supernova remnant known to have exploded in the late 1600s. It was known from optical observations to be an oxygen-rich remnant, which means that it was from a massive star collapse, not from in-spiraling white dwarfs. And as a result, we expected that it should have created a neutron star, or perhaps a black hole, likely a neutron star based on its estimated mass. And that neutron star was had never been identified, despite this being a very bright radio source, well-studied optical source. The first Chandra observation revealed that quite simply, and you can all see that little dot in the middle. That is that young neutron star. That's a really nice achievement. For somebody like me, it's also a complete surprise, because this is what young neutron stars are supposed to look like. At least that's what we thought. And this is a wildly bright source. The ACES people don't like it when I ask to observe the Crab because it's so bright. That is not at all what that neutron star in Cassiopeia A looks like. So that observation not only identified the neutron star, it identified a new subclass, if you will, of young neutron stars. Others of these so-called central compact objects have been discovered in supernova remnants since. If you look at the spectrum of the entire supernova remnant, you see that it's rich in lines, as many of you would expect from a hot shocked plasma. Those lines are predominantly from the ejecta of the supernova explosion, and their abundances tell you something about the progenitor star. Because of the imaging spectroscopy capabilities of the ACES detector, one can decide to color the different energies of X-rays in different colors to make a 3-color image, and you've all seen these kinds of things. This immediately told us some interesting physics, just looking at the image about Cassiopeia A. First of all, you see that blue ring all the way around the outside of it. The blue is the high energy stuff in this image, and if you take a spectrum of that and look at it, you find out that there's no emission lines in it. It's just a continuum. What it is synchrotron radiation from electrons with energies between 50 and 100 TeV. So this is an identification of where the forward shock of the supernova remnant is accelerating cosmic rays to very high energies. The purplish stuff that you see over to the lower left, to the southeast, is dominated by iron L. And we all tell our students that when stars collapse, massive stars collapse, they end up with an iron core that then doesn't support the pressure, and the whole star collapses and crushes the core and blows up. So you would expect, why wouldn't that iron be in the middle? And it's not. It's definitely turned over in some sort of very turbulent convective overturn that has to be part of people's supernova models that they do if they want to actually conform to reality. You can also go individually through the supernova remnant, identify the composition of the material, look at the emission measure, get a total census of the mass of the ejecta in this supernova remnant. And if you compare that total census with the expansion, which we can observe by looking at it over time, and apply some dynamical calculations, you say, well, interesting. It seems like there's about 3/10 of a solar mass missing from the X-rays. Where could that possibly be? And the answer is that this ejecta material is heated from a reverse shock that comes in, and that reverse shock hasn't gotten back all the way to the middle yet. So there's some of the material that's cold and unshocked, and that completes the census. And how could you possibly complete the census? How could you find that cold gas? Well, you could look at it in the infrared with JWST, and indeed, one finds cold unshocked. I don't think I better not play with the mouse, but there's an arrow pointing to where there is cold unshocked ejecta discovered by JWST. There's as well as a lot of other stuff that I don't have time to talk about. Staying for a moment inside our galaxy, but getting deeper into the potential well here. We know from looking at binary sources with black holes in them that the accretion process can be very, very rapid. In fact, it can be rapid enough that it's a question about how one can actually dump enough angular momentum to let the stuff actually finally traverse the path and become accreted. And so a question of how that angular momentum is dissipated is of considerable interest, not just for these kinds of sources, but for any accreting black hole sources. And this HETG observation of an accreting black hole system shows a continuum from the central source with a bunch of superimposed absorption lines that are all blue shifted. That's a result of an outflowing wind in our direction, absorbing photons from that central source. And so that demonstrates immediately that we have a mechanism for carrying away some of the momentum. And then it raises the question of what's the mechanism that generates that wind. The spectrum here shows that the ionization state of that gas is such that it is so highly ionized that there's not enough opacity for that to be a radiation-driven wind. In addition, the calculations of what density one would need for this to be a thermally driven wind give values that are much lower for the density that is than is observed. And so the conclusion from this study is that for these types of systems, or at least this system, the wind appears to be magnetically driven material that is coming over the Roche lobe and being accreted and carrying with it magnetic flux, is creating some sort of turbulence in the disk that is then generating a turbulent magnetically driven wind. Of course, we know that these ultra compact objects in binaries can, when we're really lucky, and it happens to be August of 2017, coalesce and give us a gravitational wave signal, right? And so when we had GW 170817, the in-spiral of two neutron stars, LIGO saw this wonderful result, and every telescope ran off to look at the position of this event. And the box, the black box on the top on the left, shows a Chandra observation taken on August 19th, and you see that there is nothing there whatsoever. A week later, Chandra looked at it again and detected the source quite clearly, and the inference of what's happening there is that the coalescence of these neutron stars created a hypernova explosion that generated a very powerful jet, but that jet was off axis from our point of view here, so we don't see the X-rays from it instantaneously, but eventually that jet sweeps up a bunch of material. The emission from that hot material emits over a larger angular range, and then Chandra was able to see it. And so then that material expands out. It eventually drops in luminosity, so you have a model for the behavior of that afterglow that has the flux declining with time. That's what that solid blue curve in that plot is showing. And the circular points are showing the Chandra observations that follow the behavior of GW 170817 as a function of time. And you see it follows it quite nicely until it doesn't. And suddenly one can still see the source, even though the model says you really shouldn't be able to. And the thought is that there's another underlying emission component, possibly emission from the hypernova itself and the material that it swept up, or possibly from a magnetar that was formed in that process that has been hovering below that bright jet afterglow. And only after the jet faded enough were we able to see that component. At that stage, Chandra was the only telescope, not just the only X-ray telescope, the only telescope that was still able to see emission from GW 170817. And we have an observation of that scheduled, I think this week. It might have been last week. I can't remember. Moving from there to looking at supermassive black holes in the centers of galaxies, this is an image of the center of our own galaxy and Sagittarius A star, the supermassive black hole in the center. For reference, in this image, you can see a line delineating the galactic plane. You can see some lobes of gas to the upper right and lower left of that plane. This image is again colored so that low energy X-rays are red and high energy ones are blue, so that fuzzy emission is some cooler, still X-ray hot, but cooler gas that appears to have been perhaps ejected from the central regions of the center of the galaxy. If you look right at Sagittarius A star, you find out it is ridiculously faint. For something that's got a healthy 5 million solar mass black hole in the center, there is not very much activity. In fact, if it turns out that there's a magnetar right nearby it that went into sort of a higher state, and so this little inset shows you that magnetar, and every once in a while a flare from Sagittarius A star. Makes it pretty difficult to see Sagittarius A star if you don't have a really high resolution telescope. The plot on the top shows observations, many observations taken over a long time, with gaps in between them that have been excised and pushed all together. And so you see a bunch of flaring activity and then long periods of not much activity at all. So you can see that on the left, I've taken one of the regions of where it is active and expanded to show some flares that are 6, 8, 9 times the sort of quiescent level. But most of the time, this supermassive black hole is quite inactive. But of course, as I mentioned, there's these globes of hot gas that seem to perhaps have been ejected in previous episodes of activity from the center of the galaxy. And that's the kind of thing that we see evidence for in other galaxies as well. This is a Hubble image of M87, which is an elliptical galaxy with a larger supermassive black hole in its center, and it has this really amazing jet coming out of it that's produced from accretion onto the supermassive black hole. And if you look at it with Chandra, you see a lot of structure. You can expand that jet there to see individual lobes. Those are observed to move over time when we observe it over several epochs. But also, if you kind of burn in that image, you'll notice that there's these lobes coming out, these plumes from previous jet activity, presumably. So like with the Sagittarius A star, there's evidence that in previous epochs there was big outbursts. Those have displaced gas from the center. In fact, if you look at it for a while, you can even see that there's a big, really big one from an outburst that was probably about, I forget, 12 million years ago. This, of course, is something that has become recognized in clusters of galaxies and solved a kind of an open problem that existed before, understanding why it is that when you have dense material in the center of a cluster of galaxy that is therefore cooling, why the material around it doesn't then just flow into the center and generate overdensities where you can get new star formation. That's seen sometimes, but in many clusters it's not. And this image of the Perseus cluster carries on what I was saying before by demonstrating what's going on. You have episodes a long time of massive outbursts and long-lived outbursts from those central supermassive black holes that displace a lot of gas and fight against the star formation that I was talking about. Finally, moving towards structure and cosmology, this is another image of a cluster of galaxies. This is a Hubble and ESO image of a cluster that shows all of the individual galaxies. And of course, you know that by looking at all of those individual galaxies, if you look at quasars or galaxies from behind the cluster, the gravitational potential of the cluster itself will distort them from gravitational lensing. So you can do a study of this and actually figure out where the mass of the lens is that's doing that distortion. And that, of course, is going to be dominated by not these galaxies, not even the hot X-ray gas that I'll show you in a second that permeates these clusters of galaxies, but rather by the dark matter that is within these clusters. And so these blue blobs are not emission, they are models of where the mass is centered in this cluster. And you can see, it's not a cluster, it's a pair of clusters that are merging, okay? And these dark matter condensations indicate the centroids of the clusters that have merged. The X-ray image shows the hot gas that's been stripped by the other galaxies, stripped from the individual galaxies, and fills the gravitational potential of each one of those clusters. And you can see that they've merged. You can look at that one on the right. There's a bow shock from it kind of plowing through gas. But the other thing that's really interesting and important is that the X-ray emission is offset from those from the dark matter mass concentrations. And why is that? Because dark matter only interacts gravitationally. It doesn't interact in any other way. Whereas when the X-ray emitting gas comes through and collides, there is essentially a viscosity that wraps up the gas and makes it very chaotic. It is, I like to describe the scenario as the dark matter is like two ghosts coming through and going through one another, but this is more like two ghosts that were carrying cats. And so the ghosts go right through, but the cats stand snarled up in the middle in hot X-rays. Finally, almost finally, onto dark energy. I'll go back to that slide. The dark energy acts as a sort of a positive pressure. So when galaxies are condensing into clusters, the dark energy kind of fights that a little bit, and it makes it hard to form very massive clusters, harder to form than if it wasn't there, for example. So if you take a look at the distribution of cluster sizes, this is a plot of size distribution of clusters in the 0.025 to 0.25 redshift range. It is fits to models, to a model with no dark energy, with omega lambda equal to 0. And based on that, if you then said, okay, so what would I expect from this model out at larger redshift at 0.55 to 0.9, you would expect something along that blue curve. What Chandra observes from looking at a lot of clusters of galaxies in that redshift is this. If you, on the other hand, put the omega lambda of 0.75 in, then you get a very good representation of the data. So this is a demonstration by looking at cluster size over redshift of the existence of dark energy. Finally, pretty sure, this is a cluster of galaxies. Again, for those of you who love clusters of galaxies, I hope you're happy that I've represented them well. Observed with Hubble, some strategic clusters that are good candidates to act as gravitational lenses, in this case magnifying glasses, to look at things behind them, okay? And so JWST looked through this cluster of galaxies, and it identified individual galaxies at redshifts as high as 10 by using the magnification of this cluster itself. So Chandra followed up on that, and the boxes and the insets in the upper left-hand corner show, the right one shows the JWC detection of a galaxy at redshift of about 10, and the left one shows a detection by Chandra of X-ray emission from that galaxy that is consistent with it being from accretion of a supermassive black hole of about 40 million solar masses. Now, you know, we've been talking about supermassive black holes and galaxies all along, so what's the big deal here? The big deal here is that this is at a redshift such that we're looking at about 500 million years after the Big Bang. So how do you get 40 million solar mass black holes formed that rapidly? We think of supermassive black holes as perhaps being formed by stellar evolution and eventual condensation into centers of galaxies over many epochs of time. This suggests that the likelihood is that there is, at least in some cases, heavy seeds in the early universe that create very rapid formation of supermassive black holes. So I know that's a whirlwind. I'll wrap it up here by saying that that Chandra has established the power of high angular resolution in X-ray astronomy. It's now an integral part of what we do in all of astronomy. Chandra is continuing to do this. It remains healthy. It's in high demand. It's capable of operating into the next decade and beyond. So it is what I consider right now to be the current future of high angular resolution X-ray astronomy. That is the only future of it right at the moment. I note that the effective area of Chandra is about equivalent to a 16-inch telescope, optical telescope, okay? It would be nice to have more effective area. XMM knows this. XMM has shown us that effective area is also our friend, and we're going to hear about that next. The future demands more than what we have. It demands large effective area. It demands high angular resolution. You're all here to talk about that. Axis is that upcoming future. And I'll leave it there and see if there's any quick questions.
questions? I'll ask one very quickly as people are thinking. So what are kind of the discoveries and what Chandra has actually been doing over its history? What are the ones that are kind of most different from what you expected to be doing with Chandra?
Certainly discovering supermassive black holes at a redshift of 10 is not something that was in our initial science document. There's no question about that. I would say that it was pretty surprising that we've also detected X-ray emission from every planet in the solar system except Neptune and Mercury, which we can't look at because it's too close to the sun. That was a surprise as well. I mean, detecting X-ray emission from Pluto, nobody thought that was happening either. There's many examples, but those are a couple of extremes.
Yeah.
Thanks, Matt and Mike, and thanks, Pat. You didn't say anything about the future of Chandra in the light of the budget cuts, and I wonder if you could talk about that.
Well, we don't have a lot of time here. There's not enough beer and it's too early in the morning, but you know, the situation is that Chandra has been undergoing re-budgeting exercises for 2 years going now, and was in the death throes a little bit over a year ago. And thanks to the community, really, and then ultimately Congress as well, and NASA, you know, it's still running the way that it has been all along. But the budget situation that we see at NASA right now is threatening for Chandra. It's threatening for many of the missions that we know. And unless there is something done to increase the amount of money that the Astrophysics division gets, I don't see any way to continue Chandra or a lot of other missions. On the other hand, if there are continuations, for example, we're in a continuing resolution from fiscal year 24 right now. If that were to continue, and who knows if it will, then I think that there's still possibilities. But the next several months are really going to tell us a lot on that front.
Thanks for a really nice talk, Pat. So one of the, when you think about one of my own fields, one of the legacies of Chandra and XMM undoubtedly is feedback in clusters. I mean, right from early on in the mission, this was, you know, such a became such a dominant narrative about feedback. Was that in the original Chandra science case? Was there any discussion of that in the original case?
You know, I don't know about that, Chris. I'm not aware of it. Maybe there was, but I'm not aware of it. In the early case, there was a lot more talk about using clusters to, you know, clusters, they're such beautifully relaxed, you know, steady pressure systems that you could do a whole lot of measurements of dark matter distributions and such. And obviously that becomes very complicated when things look like the kinds of things that you spend most of your time looking at. I'm not aware that that was anticipated, but I'm not a cluster expert, and I wasn't around when they were writing the early science case. I started on the mission in, you know, like 11 years before it launched, but it was earlier than that they were writing it.
Thanks.
Yep.
Questions? If not, let's thank the speaker again. You can turn.
I got it. I think, can you hear me? Okay. I do have water here because often I get really dry throat when I'm talking, so I may need to take a drink occasionally. So I'm here to talk about XMM-Newton. I want to thank Chris for the invitation to give a talk. Next week, we were supposed to have our 25th anniversary conference, but we had to cancel that. So this is my opportunity to give you a little bit of flavor of XMM from the past to the present. This is a new animation we just had created to show, it's a beauty shot of the satellite. XMM was launched on December 10th, 1999 in French Guiana on an Ariane 5 rocket. It has 3 telescopes and Chandra has 1, so that's one difference between XMM and Chandra. This is an overview for those of you who don't really know the instrumentation. We have 3 imaging cameras called EPIC, 2 MOS detectors and 1 PN. We have a reflection grating spectrometer, the RGS. Sorry, I can't look sideways or my voice will not pick up on the mic. We have an optical monitor that was supplied by the US. So we have the optical UV coverage as well as the X-ray. And our strengths are the large collecting area, like we just heard, as a primary strength. We also have the simultaneous optical UV coverage, large field of view. It's approximately, I think, what AXIS's field of view is going to be. We also have a highly elliptical orbit, which allows long continuous time coverage up to 130 kiloseconds at a time, and decent angular resolution, good enough for some science, but not all. And just so you know, in terms of the US participation, XMM is a NASA-ESA partnership. We, the US, provided instrumentation and hardware, the RGS and the optical monitor. We also currently provide calibration and software support. NASA has a general observer facility, the GOF, the XMM GOF, which I lead or oversee, and the GOF provides software and user support. So most of you would probably interact with us rather than interacting with folks on the ESA side. This is just a slide, don't even have to read it all, but it just shows, our key enabling capabilities scientifically, based on the decadal themes of worlds and suns in context to cosmic ecosystems. So we do exoplanets, solar system science, all the way to, like large-scale structure and surveys. So this is just showing XMM's strengths. And then I wanted to mention that what is it that we can show as a, pathfinder, I guess, to AXIS. So AXIS versus XMM. The 3 pillars of the AXIS team science program are seeds of supermassive black holes, how do gas, metals, and dust flow into, through, and out of galaxies, and what powers explosive phenomena. The capabilities of AXIS compared to XMM, about 10 times better PSF, 4 times larger area below 2 keV, and you can see on the effective area curve that at around 6 keV, which is critical for a lot of, for example, AGN science that I work on, AXIS and XMM are kind of comparable. So the kind of science I show here can be done absolutely with AXIS. Similar field of view, but with a stable PSF across the field. So you can get really nice images of large-scale structure without having the degradation of the PSF off axis, which you get with XMM. I'm going to focus here on axis-type science. So I specifically excluded stuff because AXIS won't do it because it has different instrumentation. But I really want to display here where I think AXIS can improve significantly over XMM. So this is going to show you a glimpse of what I think AXIS can do better. So I'm going to also do it a little bit with time. So I kind of picked my favorite things. This is in no way inclusive. The disclaimer is if your stuff isn't shown here, it doesn't mean anything. I just picked stuff that I kind of liked and felt I could talk to, and things that showed off the capabilities. So in the early years, of course, we were really focusing on things that showed off our ability for large effective area and large field of view. I stole this slide from Brian Williams. I think I saw him here. From the 20th anniversary symposium, because I really liked it. So it just shows, across large things like 30 arc minutes across, we were taking images, beautiful images of supernova remnants up to sizes of 4 degrees so we could tile across the sky. And so in the early days, people were really focusing on science like this. So you could get narrowband imaging. Here's a slide of N132D with its RGS spectrum showing you how you could split the supernova remnant out into emission line maps. Also Tycho, same thing. So this revealed the complex spatial structure. And even though we're not Chandra, we could see complexities on larger scales out to the edges of these things simply by looking at them one time. We didn't have to take multiple observations. I really like this one because it shows the evolution of how you get what you get with more collecting area. So on the right-hand side in 2004, there's your nice picture, color-coded picture of SN1006. The non-thermal emission appears white at the edges because you get the same intensity all the way across in the different colors. But sorry, that was the left-hand side. On the right-hand side, 2015, you see the same supernova remnant. This time, there's enough signal by now to get to all those little regions there. They were able to extract individual spectra based on the photon counting statistics, and they got 3,596 spectra out of this one supernova remnant. And you could do things like create an iron map, like the magnesium equivalent width map I show, the electron density map here. So they could create all of this in terms of mapping it out. And they found that the outer shells, for example, have lower temperatures and densities, indicating recently shocked ISM. But I think this really demonstrates the power of XMM's ability to gather photons. Another thing people were doing was looking at stars. So one of the first stars that we studied was Proxima Centauri. So this on the left-hand side, you see the epic X-ray light curve, and then you also see the optical monitor U-band filters. So they were able to study it in these two wave bands. On the right-hand side, you see the epic PN spectra during the different stages. So the bottom curve is the pre-flare in the black curve, and then the others are during various flare stages. And what they find is there is continuously variable X-ray emission on different time scales. And so the result here is that there's a low level of emission from magnetic, I haven't heard him say, magnetically active stars like Proxima Centauri over a large range of energies. This is a survey of a large field, so just think about the Orion Nebula. This is a survey of the Orion's belt region. On the right-hand side, you see the XMM image, and there are several pointings here covering that entire region. The little circle in the middle is where Chandra observed it. I don't show that, but that was the very center where Chandra can do a lot better. But this is the Orion A molecular cloud. It's a 3 by 1 degree region. In the middle is, and so this is the Spitzer, it's called the Survey of Orion A with XMM Spitzer, the SOX program. And the IRAC color magnitude diagram splits out the different categories of stars. And also you can find the background AGN hiding around in this field. But the goal here was to complete a census of evolved young stellar objects. And so they found about, 700 or so sources here, and they did this study. But this shows, again, the power of XMM's ability to look at large fields. Galaxy clusters, I'm not going to spend as much time as Pat did because I don't know as much about galaxy clusters myself. But this is a study done by Steve Snowden et al. To be able to also understand the X-ray the detector background on XMM. So Steve created a catalog of these cluster images, but he went through and found a way to screen the data really, really well for periods of background like like the particle spectrum and background enhancements, and was able to create something that we now call the Extended Source Analysis Software System. So that's ESAS. So this was developed by Steve using this technique in 2008. And on the right-hand side, you can just see the temperature map scaled with radius and the abundance. So there was a lot of science that came out of this, but a lot of it went into calibration for the XMM team. And the US provided this software to ESA. Perseus, I'm showing that too. This is an XMM and Chandra composite. So you can see, of course, the really nice Chandra image of Perseus, but on the left-hand side there, you see this giant arc. It's about 730 kiloparsecs out. And this is a giant cold front, which is about 5 gigayears old. So it's really, really old. It came out of the cluster a really long time ago. And basically, these ancient cold fronts arise outwards from the cluster core. But this also shows XMM's ability to really gather low surface brightness features on a much larger scale. And Chandra did actually follow up and look at that cold front on one of the edges and found a very like a very sharp edge to it. So, often what I've seen in the literature is that XMM might find something, and then Chandra's like, oh, we'll go follow up on a smaller part of it and to study it in more detail. I like this one because it's pretty. It's a galaxy group. And in the image, you see the hot gas in blue, the iron atoms. The iron is in purple that comes out from the supernova explosions, and radio emission is in the teal color. So the radio emission is filaments left over from supermassive black hole jets, possibly. But the hot gas is not evenly distributed here, probably due to sloshing from collisions from other galaxies that are not in the image. But it just shows a lovely picture of a smaller system with seeing the diffuse emission here and what XMM can do with fainter systems. Now I'm going to get into AGN a little bit. So the iron K alpha fluorescence line is a really good way to study AGN. It's at 6.4 keV, and then it's pretty ubiquitous in AGN, essentially. And you can get iron emission from reflection off of various regions, like the accretion disk or the molecular torus. And the idea is to look at the iron line profile and see what you find in terms of variability and understand where it's coming from. I really like I'm not getting into any, I'm being agnostic about the iron line. I just want to show you the data because there's still a lot of controversy over what's really going on because it's very complicated. But the left-hand side shows for NGC 3516 kind of the energy of the evolution of the flux across time in the line profile. So the middle image is the line profile at different epochs. So you can see in that middle region image that the wing, the little red wing goes away and then it comes back. So you have two profiles. So there's variability there. And if you map that with time, you can see on the right-hand side the like squiggles. And that's how that red wing comes and goes with time. And then a bottom image on the left-hand panel is the model for iron K alpha being produced by an illuminated spot on the accretion disk and modulated by Doppler and gravitational effects. So this is kind of the typical thing of what we would expect from an accretion disk. So these data, even though it might not be extremely high significance, suggests that we're really seeing that in this source. On the right-hand side, kind of similar science, deviations in the iron line flux. Here you can see all the squiggles. And so these red and blue wings are moving around. And Jane Turner et al. Modeled this. And it appears to be something that's consistent with emission from matter in a Keplerian orbit around a supermassive black hole. So once again, we're saying, oh, we see something from the accretion disk. That's really cool. This one I really like too because it has even more complexity. Arcarian 120, we're measuring accretion disk hotspots here too, and you can see in the picture in the middle, the blue, the red dots show the red wing, the blue wing, and the different profiles at different times. On the right-hand side, again, you've got the structure of the line over time with energy. The streak in the middle is the center, basically, but you see the wiggles on the edges, and that's the red and blue wings coming and going. And so in this case, the iron K alpha line also seems to be coming from around an inner accretion disk around a black hole. There are many other cases of things where we don't see iron lines from accretion disks, they come from somewhere else. But this is really powerful science that XMM did really, really well. And I think with AXIS, we'll be able to continue to study these emission lines and finally maybe come to good conclusions for large samples about reverberation mapping and accretion disks around supermassive black holes. Now I'm going to switch to so we're coming toward toward the current state. So this is like this is roughly 2013. So we're kind of in the middle of the XMM mission, and we're starting to get some more exotic discoveries. In this case, it's about a pulsar. So for this pulsar, what you expect to happen is the X-ray emission should follow the radio emission. So the pulsar models predict a certain rhythm for the X-ray emission. In this case, they looked at this pulsar, and you see in the upper part that the X-ray emission was gone when the radio emission showed up, and in the lower part of the image, the radio emission kind of went away as the X-ray emission showed up. So when it was switching on and off, the radio bright phases were opposite of what they should be. So you should see these somehow correlate, and that wasn't happening. So this kind of reignited the debate over the actual physical mechanisms that drive pulsar emissions. So it was a pretty neat result from XMM. This is now looking at the center of the Milky Way. We already heard a bit about Sagittarius A star, but this is on a much larger scale. So if you go out to much larger scales, there are these Fermi bubbles below the plane. XMM was able to detect X-ray structure kind of connecting these, and they're calling them the galactic chimney. But they're believed to be evidence of matter and energy ejected from previous episodes. So when we saw these flares with Chandra, maybe in the past, there were much stronger flares and you were getting ejections over time. And this might be the accumulation of that energy and momentum moving outward. But it's really nicely aligned. And on the left-hand side, you can see a little cartoon that shows these different lobes or chimneys going up and down. Okay. So this is one of my favorites, talking about feedback, but this is about galaxy halos. And I like this one because it shows how much we need more data. So this is the Galaxy NGC 891, and the Chandra image on the upper left shows the halo in red, and then on the upper left on the right-hand side is the XMM image. You can see right away that XMM detects more emission further out. That's really neat. But on the very right-hand side, the color-coded image, the red in that image shows just the oxygen line. So Edmund was able to separate out an emission line map for this galaxy halo, and that's going to give you some information about how that halo was formed. But what also is interesting is he was looking to find the gas metallicity, because that's going to tell you the difference between models for these outflows. He was able to get good fits for a model with one thermal component, which ruled out solar. So for that fit, it was like much less than solar. But then a 2-temperature fit worked just as well. And I know this because I've done this stuff with other objects with data like this. And so you can't distinguish between 2 temperatures or 1 temperature. If you have a 2-temperature model, you can have solar abundances. So you need access. We need access to be able to get enough data for galaxies like this to be able to distinguish between multiple temperature fits and to actually measure these abundances. So I think this is a very important source for future observations with access. Now we're coming more to the present. So recently, one of the XMM Heritage programs was awarded to Neil Brandt, and this is his and his team's heritage program, a survey of the Rubin LSST deep drilling fields. And you can see here a couple of fields from that survey, left-hand side, also compared to the size of the moon. So you can see how much of the sky they were able to get in this 2 or 3 year survey covering this region. The XMM serves, it covers 13 square degrees and is at a 50 kilosecond depth. Okay. And so what they're aiming to do is study supermassive black holes and all kinds of things across the universe. And so this is a really powerful data set. Cosmic ecosystems, this is one I like. It's an orphan cloud of hot X-ray gas that's found within a galaxy cluster, not near a galaxy itself. So it indicates that the stripped ISM can survive for long periods of time. And this is another kind of faint X-ray fuzzy thing that XMM discovered. We also are able to kind of study the ISM and by looking at gamma ray bursts like this one, which was the brightest one ever detected so far, and XMM was able to make images across time to show the evolution of these dust scattering rings that come from this observation. So the dust is in the line of sight, and the rings tell you where the dust actually is with respect to between you and the gamma ray burst. And so also you can measure the differential extinction, and on the right-hand side is a plot that indicate distances and widths of the dust layers. So you can use the X-ray satellite to do this sort of thing for large, very bright bursts like this. Now, going into what is now big with XMM, these last two topics. So over time, in the beginning, we weren't really thinking about studying stars as much in terms of exoplanet habitability, of course. That's become a newer topic. So now XMM is doing a lot of work characterizing stellar flares of exoplanet hosts to try and understand the impacts on those exoplanets. This is a study using XMM and Chandra observations of K&M dwarf stars to model the stellar flares to understand how those flares would affect the photolysis of ozone. So what's going to go on in the atmosphere, and how good is that or bad is that for the planet that's trying to form there? And on the right, I just show the cumulative frequency of the flares. But this is becoming a really hot topic for XMM. And then here's another kind of exoplanet thing. It's a sample to look at a bunch of M dwarfs and study the SEDs all the way from the optical IR to the X-ray. And on this image, you can see that the sun is the yellow curve, and the M dwarf stars have much more X-ray emission. So, this flaring activity is really, really important, and XMM is turning out to be doing a really great job at this science. Then I've got to throw in an AGN WINS RGS slide for anybody who wants to see cool wind structures. So the RGS on XMM can study high velocity outflows from the accretion disk, and this is AGN activity from winds down in the center of AGN. And then finally, my last topic is another very growing category for XMM, and this is time domain studies and things like quasi-periodic eruptions and QPOs and things like that. There have been more and more studies, and also across longer timescales because we have a 25-year baseline. This is the XMM discovery of quasi-periodic eruptions from a galaxy center, and you can see the periodic signal on the top are 2 XMM observations, then on the bottom in the red is a Chandra follow-up. The leading model for these QPEs is that the flares are caused by stellar mass objects orbiting a supermassive black hole and colliding with the accretion disk. And if that's really true, then these should produce gravitational wave emission that can be seen with LISA. So this is really important in terms of looking at precursors for LISA. And then finally, another really cool result that I think was cool, we actually see light bending from behind a supermassive black hole. Basically, if you look in the center, that's the XMM light curve, and then the new star one on the bottom, but you can see the flares in the XMM light curve. This group studied those flares in detail, and on the right-hand side, they split the spectrum up into energy bands that correspond with the continuum, the blue wing, the center of the iron K alpha line, and the red wing, or maybe it was the opposite, red, center, blue. And you can see that the spectra are different. And there are little gray lines that are hard to see, dotted lines. And that's where they see additional peaks in the emission that were like unusual. So they went in and modeled those, and it turns out they can be modeled just by having the reverberation effects of the iron K alpha fluorescence line bouncing off the other side of the accretion disk and then coming around the black hole to our line of sight. So you have the reflection coming at you directly, and then something that bends around the accretion disk. And, this is showing you, I think, that there's so much work that can be done for large things, for faint things, and then these detailed studies of variability, and also the new stuff with exoplanets, I think, are really critical for AXIS. So I'm just making the case, the AXIS people, that if these aren't in your science pillars, maybe they should be. Anyway, thank you very much.
Okay, we have time for a few questions. So maybe I'll ask something for you. What was the kind of most exciting discovery from XMM?
I was shocked that we were able to look at exoplanet transits in X-ray.
Yeah.
I was just like, wow, because I remember doing that with Spitzer, and that was a big deal thing, and it was so obvious that you can do it in the IR. But when we first saw those in the X-ray, it was just shocking. I thought that was fascinating.
Okay, other comments or questions?
You mentioned this once or twice, but I'm curious, what is the what are the sorry, let me start again. You you talked about how there were a number of cases where XMM would observe something and then Chandra would observe it, and you get the benefit of XMM's collecting area and then Chandra's angular resolution. Can you think of, I'm just curious, which of the sort of science topics that you've mentioned here are the ones that would benefit most from having both of those capabilities at the same time?
I think, yeah, galaxy clusters, really. I could also say AGN, but with Chandra, we still can't really resolve as much as we want to. But I really think the cluster science it's critical to have both.
Okay, any other questions? We can move on. All right, if not, let's congratulate the speaker.
Thank you.
Actually, is this one on?
Yeah.
Hi, everybody. I'm Ryan Hickox from Dartmouth College. And first, I want to say thank you to the organizers for the invitation to come talk to you about wide field multi-wavelength surveys and how they tie into the exciting science with AXIS. I'm here partly in my role as one of the co-chairs of the committee that defined the high latitude wide area survey for Roman, which I'll get into, and also as a member of the Roman Observations Time Allocation Committee, which just released its report about the Roman recommendations, a Roman observing plan a couple weeks ago. And so I'm going to focus somewhat on Roman here and talk a little bit about the synergies, but I'll also give you a sort of bigger picture. So in terms of outline, I'll just give an overview of something we've talked about a lot already, which is the connection between black holes, galaxies, and dark matter halos. And then I'll sort of describe the advantages of why you would want to do wide field surveys to study this stuff, and also why you want really good multi-wavelength coverage. I'll then give you an overview of the Roman high latitude wide area survey, and then think about some of the synergies potentially with AXIS. Okay, so first, just to start off, AXIS has planned extragalactic surveys that will be both deeper and wider than those that are planned for, or those that exist already with Chandra and XMM. So we heard about Chandra and XMM's amazing legacy and AXIS, and we'll really build on that for a wide range of science. And in terms of the AXIS science pillars that we saw yesterday, we're going to focus on really the first two of these. What causes supermassive black holes to grow into the ones that we see around us today, and how do they influence the material around them over the history of the universe? So to study this, it's one thing I like to think about, or like to sort of begin by thinking about, is actually, what's our best understanding of what's going on in terms of how black hole growth and galaxy growth all scale together with their dark matter halos. And so we have simulations that show how this all works on a wide range of scales. This is a nice visualization of a simulation by Daniel Angeles Alcazar that's zooming way into the accreting material right around a black hole, and then zooming way back out to the scale of the dark matter halo that this galaxy lives in. And you can see that this is a really complicated process. There's a lot going on. There's a lot of gas moving on all different scales, both in space and time. And there's things like star formation and feedback and other processes, highly nonlinear processes that are going on throughout this whole process. So this is a tricky thing to study observationally, especially when, even with really good angular resolution, you can't necessarily resolve right down to the center of this kind of object. Just to point out that this is a multi-scale problem, not only in space, but also in time. This is an old visualization, but a nice one in terms of the way that they presented it from the illustrious cosmological simulation. And this is showing both dark matter and gas in galaxies. And you can see directly the dark matter feedback going on. The colors here represent the temperature of the gas, and you can see, the black hole feedback, these big outbursts happening on timescales. Now this is evolving over a way longer time scale than the one I showed earlier, over something like 1 billion years. And you can see these sort of quasi-stochastic outbursts from the black hole that are having a big impact on what's going on around them. So the key takeaway from this is that if we're trying to understand black hole evolution and its impact on the stuff around them, this is a highly multi-scale problem in both space and time. And especially when we're thinking about what's going on with black hole accretion, I think people who have been around me for a while know this. We've been talking about it for a long time now, but it's really important to think carefully about the fact that what you see in a accreting black hole system at any given moment will not necessarily be what you would see over a long time frame, especially over the kind of time frames on which galaxies evolve. So we know that, or even much longer than a human lifetime, we know that AGN vary a lot. And so we can see light echoes both down in our galactic center or on larger timescales in, for example, the Fermi and E Rosita bubbles that we just heard about. You can also see light echoes from sort of ionization regions outside of galaxies, like a Verwerp that we have here, or in things that look like light echoes within galaxies, like has been observed here with NGC 1068. And the main takeaway is that we know that black holes vary significantly in the rate at which they accrete and the amount of energy that they give off. And this is a somewhat complicated, somewhat stochastic process. Another way of visualizing this is we know, by the way, simulations show that this should be the case. This is a plot from a paper of mine from a while ago showing on the right, it shows the predicted black hole Eddington ratio as a function of time over about 80 million years. And you vary from something like Sag star, 10 to the minus 7, so basically completely quiescent, all the way up to Eddington on that time frame, with over time scales of thousands to millions of years. And so something that might be a normal galaxy a lot of the time might be an AGN another part of the time. And this process is kind of stochastic. So you can think of, when you're watching a black hole grow, it's sort of like a fluorescent light bulb flickering on and off, and less of something that just turns on and then turns off again. What this means is that in order to study this, we have to think about it statistically. And I'm not going to go through this slide in a great deal of detail. This is a nice figure from James Aird that's part of a review that he and I are writing with Dave Alexander that will actually be coming out later this year. But this emphasizes the point that when you have a black hole flickering on and off all the time, what you get is a broad range of accretion rates for any individual system. And that manifests itself in a lot of scatter and complicated and somewhat sometimes counterintuitive behavior in the relationship between the various observables and the various black hole observables, like the instantaneous accretion rate, and things like stellar mass or star formation rate. And Neil talked about some of this in detail yesterday, but just emphasizing this fact here. So what you need to do is handle this kind of thing in a statistical way. And Neil gave some examples of how you could do this. I'll just show a couple here. if you want to look at the connection between star formation and black hole growth, you need to average over a bunch of black holes in order to smooth out those variations, or you need to have, which is something that was done on this left-hand plot here, with the big points show the averages of the accretion luminosity as a function of star formation rate, and they're pretty much 1-to-1, showing that there is some, on average, some connection between those things. But if you really want to understand what's going on, you need to look at the whole distribution functions. And this is something that a number of groups, Neil's group, James Aird, and some others have done a lot of work on actually measuring whole accretion rate distributions as a function of various properties. So the key is that understanding how black holes grow means you want as many sources as possible. It's a statistical problem because you can't necessarily just correlate one object 1-to-1 with another one. Okay. Another thing that's really important when thinking about understanding growing black holes is that they inhabit a very broad range of cosmic environments. The best understanding we have now is that black holes grow along with their galaxies sort of on average, which means that they're broadly found in all kinds of different cosmic environment, all kinds of different dark matter halo masses. And if you want to understand how black holes inhabit their dark matter halos, you need to incorporate this stochasticity, and you need to be probing a wide range of cosmic environments in order to do that. So this is a figure from a nice paper by Meredith Powell, who is modeling both the correlation function and the luminosity function, the spatial correlation function and the luminosity function for, in this case, Swift bat selected AGN, and showing that you really need to consider, all of these things together in a statistical way. And she has a nice model that uses some very simple assumptions and allows you to model both the luminosity function and the spatial correlation function. But this is for sources at quite low redshift with Swift bat. But another indication of how you need to do all this stuff in a statistical way. So the point I'm getting to is that in order to do this kind of science, one of the things that this pushes you to is trying to do extragalactic surveys over a wide area. And really, I'll emphasize 2 reasons here. One is that it gives you the best statistics. So for anybody who's worked on X-ray surveys, this is sort of second nature, but for those who don't think about this that much, the flux distribution of X-ray sources, we saw a couple examples of this already in the last couple days. It has a break and gets shallower down to the faintest fluxes. So once you get beyond that break, where you're getting less and less yield as you go farther down, then deeper observations will actually yield fewer sources. They will do other things. They'll get you better signal to noise in the detections you make, or they'll get you to fainter or higher redshift things potentially. But if you're looking for the big number, just numbers of sources, then doing a wider area for the same exposure time will actually yield you larger numbers. And just to give an example, here's a table from a nice paper by Stefano from 2020, which I think uses some other assumptions about background and a different effective area curve. So the numbers are not entirely current. But the main takeaway from this is that when if you were to utilize a certain total exposure time with axis, in this case 5 megaseconds, and put it over different areas, the wide area gets you by far the most sources to work with. And so there's this trade-off that you make between wanting to go deep, say detect really, really faint things, and wanting to get a lot of sources to do your statistics. And if you're really interested in the statistical side of things, it's better to do wide area. And so hence the wedding cake that the Axis team already has planned. The other reason for doing a wide area, we've seen a few figures along this line as well, is that you just want to probe a large volume. Because especially if you're looking for a range of cosmic environments, the clusters are of order. I think it depends on exactly how you define them. Someone can correct me if this is wrong, but they're of order, say 1 to 10 per square degree on the sky. So if you want to actually get big, the most massive environments, then you need to be probing multiple square degrees in order to do that. And so also, if you want to find rare, interesting sources, then you need to go over a larger volume. Okay, So this is why you might do a wide area survey. The other thing I want to emphasize is the importance of getting lots of multi-wavelength data for surveys that you would do. This is this nice NASA graphic about what the Whirlpool galaxy looks like in all different wavelengths, and you can see all the different physical processes. We love doing these kind of things like in an Astro 101 class. And this gives you a bunch of different quantities that are really important for measuring the kind of stuff that we want to measure. So I stole the slide from Neil's talk yesterday, but if you want to measure things like stellar mass, star formation rate, galaxy compactness, or broad environment, you can't do that just in the X-rays. You need to have a really good multi-wavelength coverage in order to measure all this stuff. One other thing that's important too is that if you want to understand the nature of the AGN beyond just what you learn in the X-rays, you need to have really good multi-wavelength data. So this is a little animation from a review article that David Alexander and I wrote. It's sort of a long time ago now. That shows what happens. These are just sort of some fake images at different wavelengths. And it's what happens if you take a galaxy and then you add an AGN to it. And so here we go. The AGN comes up and up and up, and you can see that if you have an unobscured AGN, it'll, initially not dominate the galaxy at all, and then it'll start to dominate at all wavelengths. However, if you add in some obscuration, then some of these wavelengths will get suppressed and other ones will not. And so a combination of multi-wavelength indicators, say, for example, mid-infrared and X-ray, or optical lines in X-ray, or other things, are really important to fully characterize the source that you're seeing. And so this is an example, again, of why having excellent multi-wavelength coverage and spectroscopy, if you can get it in your field, is really important. Okay, so thankfully, we have a lot of wide field telescopes that have actually been able to survey over the electromagnetic spectrum. I have deliberately not put the names of the telescopes on here because I've left some off because you couldn't possibly find all the telescopes, but this is just to emphasize, and they're not exactly in the right place in the electromagnetic spectrum, so please don't get on my case for putting LOFAR in the wrong place, for example. But this just shows that there's a range of observatories that sort of cover, that are able to cover wide areas that observe across the whole electromagnetic spectrum. And we have two upcoming ones, one obviously AXIS, and then also the upcoming Roman Space Telescope, that add to this, in particular in the near infrared and the X-rays. And so that's what I'll focus on for the rest of this talk. So many of you will be familiar with Roman. Roman, we've heard a lot about the history of flagships. Roman is the next NASA flagship that's coming along. It's scheduled to launch potentially by late next year. What Roman is a near-infrared telescope built on a telescope platform that looks a lot like the Hubble Space Telescope. They were both designs for spy satellites that have the same 2.4 meter aperture. But the difference between Roman and Hubble is Roman has a much, much larger field of view. It has a different suite of instruments that are better calibrated, more sensitive, and it can slew and settle a lot faster than Hubble could by design. And so Roman has 100 times field of view, can slew and settle 10 times faster. So its survey speed is 1,000 times that of Hubble, but still having space-based angular resolution and sensitivity comparable to Hubble's near-infrared observations. So Roman is really a remarkable telescope that is orders of magnitude better than what we've had in space before. And so for those who know me from my background, my background is an X-ray astronomer. So what the heck am I doing up here talking to you about Roman? I wanted to give you a little bit of history in terms of how it got there, and made this maybe a lesson for some of the more junior people in the audience about how these things come about. So this is my first sort of big foray into working on missions was working on Lynx, the flagship that in some ways is a parallel or precursor to AXIS. So here's a meeting at the Smithsonian Castle in 2016 with a bunch of characters, many of whom are in this room. And you may wonder, where's Ryan? Why is Ryan saying he's here? Where is he? I'm obscured, but there I am. Right there in the background. So this is my first go at sort of thinking about what a big mission might do. And that was a lot of fun, and it was great to learn about all the possibilities of what you can do with amazing high resolution X-ray optics in space. Later on, as we were working on links, there was, and I was sort of more interested in NASA. Some may remember that in the president's first term, the budget line item in the president's budget request for Roman was zeroed out. It was called W First at the time. So there was a call to go to DC and go advocate for it to be funded. And so being from New Hampshire, our senior senator was the chair of the CJS subcommittee that actually writes the science appropriation bills. So we sort of had a particular role to play in doing this. So myself and my Dartmouth colleague, Robert Caldwell, we went down, who's a cosmology theorist. We went down to Washington, talked to a bunch of people. It got zeroed out again the next year. So we went back down again and succeeded again to get it back in the budget. Continue going to Washington to do various NASA-related things. And now, Roman has been funded. And Roman, just so you know, is actually a real working object. This is my some current and former members of my research group, Stephanie Podgett and Kelly Whalen, with me at Goddard in January this year, and there's Roman in the background in the clean room. We were actually watching people with torque wrenches assemble the thing. It was very cool, but it is a really, it works extremely well. The calibrations are amazing, and it really is, the testing shows that the calibrations will work really well. It is, it's still on schedule to launch next year. So I got to be, as part of all through this and part of my engagement with this, I got to work on various Roman-related things, and one of them was I ended up being the chair of the committee that defined the high latitude wide area survey, as I'll describe in a second, and then I got to serve on the road time allocation committee that made the final recommendations for the Roman survey program, and this is that group at Space Telescope a couple months ago. Okay, and so now, as I mentioned last couple weeks ago, Roman actually announced what those recommendations would be. Roman has 3 core community surveys that were defined in a community process, and together they make up about 75% of Roman's observing time. There's the Galactic Bulge Time Domain Survey that does repeated observations of the galactic bulge to do, in particular, look for exoplanets by microlensing, but a bunch of other science as well. There's the High Latitude Time Domain Survey, which observes high latitude fields many times over and over again, primarily to find supernovae to measure cosmic acceleration. And then there's the High Latitude Wide Area Survey, which is the largest of them, that observes about 5,000 square degrees to also to do cosmology, but then to do a bunch of other stuff, as I'll describe in a minute. Here's the nice little graphic they have for the High Latitude Wide Area Survey. And so this is where, for those who are interested in what fields will this be in, which is of course important for access, these are the broad recommendations for where these different fields go. And so by far the largest field is the HLWAS, that is in mostly the southern hemisphere to overlap with LSST coverage, but sort of as far north as possible. And then in addition, here are the other fields. The galactic bulge field is right in the middle, and then there are 2 high latitude time domain survey in either pole. And there's also in red, and I'll get to that in a little bit, there's the galactic plane survey, which is also a separate survey that was put together to as an early definition survey to survey the galactic plane that's still in the process of being defined. So I'm not going to go through all the details on this slide and just put it there in case anybody would like the slides later. But the High Latitude Wide Area Survey has 2 components. It has an imaging component, which is driven primarily by weak lensing for cosmology structure measurements, and also spectroscopy, which is designed to do galaxy clustering to determine baryon acoustic oscillations and redshift space distortions that determine cosmography and growth of structure And these two cosmology things were the sort of level 1 requirements that we built the survey around. But there also was a very important requirement that it's supposed to do imaging and spectroscopy to deep magnitudes in the infrared for general astrophysics science. And I think we've come up with a survey that really achieves that. So the design that the High Latitude Wide Area Survey converged on was one where we have 3 tiers. It's a little different from a typical wedding cake. This one is a medium tier that's 2,400 square degrees. That includes 3 bands, Y band, J band, and H band imaging, and also slitless grism spectroscopy. And so this will allow color information, really careful weak lensing measurements, and also gives a wide area redshift survey for both the clustering and many astrophysical applications. There were a lot of white papers that went into this community process that asked for a very wide area survey with Roman, so that's also included as well, as much as we could get in the time. There's a wide area survey in a single band, for which hopefully we can do weak lensing measurements if we can calibrate out chromatic effects, which I'm happy to talk to people about later, but also has a wide range of other astrophysics applications, including, for example, looking for galaxy clusters or studying galaxy clusters. And then, and this is important for AXIS, there's a deep tier that covers in total 20 square degrees that's designed in here for calibration of the measurements for the other tiers. And so this is a sort of breakdown of what the survey looks like and what different bands will be covered by them. And in particular, you see the deep and the ultra deep tiers. These have extremely deep measurements in lots of different bands. And so it'll be really an extraordinary data set over something like 20 square degrees. In total, we're getting something like 600 million galaxies with shape measurements. It's really kind of wild compared to what's been possible before in the near infrared. Okay, so we're going to have this extraordinary near-infrared data set, and it would make a lot of sense to have AXIS surveys actually cover some of these areas, because now you're going to have Hubble-like resolution for characterizing galaxy shapes and getting really good sensitivity for spectroscopy for redshifts and all the other things that come along with this extraordinary data set that we have. And I just want to emphasize how good AXIS is as a survey machine for doing this kind of stuff. This has been mentioned before, but just to highlight, it has high throughput compared to, say, Chandra and XMM. And also, the angular resolution being large across the field of view is really enormous. You can use the whole field of view. Together, the high throughput and larger angular resolution give you a survey speed that's something like, to a given depth, that's 70 times that of what was possible with Chandra. Also, the broad energy coverage is really important. Neil mentioned E Rosita yesterday, and that has, of course, covers a huge area, but is really limited in terms of its angular resolution is not as good, but also its and sensitivity, but it's also not able to detect nearly as many obscured AGN because its sensitivity doesn't go out as much. And lastly, just to point out that the slew times are quick enough that you really can produce a large mosaic efficiently. So this gives us a lot of potential synergies between AXIS and Roman. One is to cite the AXIS deep and or intermediate fields that have been described in these areas that will have the high latitude wide area survey deep calibration fields. You could also potentially consider doing a wider AXIS survey than the 2 that have been considered for the PI-led program. And I'm going to suggest that maybe that could be done as part of a multi-cycle GEO program, as part of the 70% of the survey that, of the observing time that goes to GEO. You can, of course, do targeted follow-up of interesting Roman sources. If we have 5,000 square degrees, there's going to be lots of interesting things that you can then potentially follow up with AXIS. And then finally, just to point out that there also is a galactic plane survey. And so if we go back to look at this whole survey area, the red thing here is the galactic plane survey. And this is one realization. It's not determined yet, but this is one realization of what that coverage with Roman would look like. And if you go in Chris and everybody's AXIS paper and look at what a galactic plane survey might look like with AXIS, it looks like that. So there's not a coincidence. This is the same part of the sky you'd want to look at, but the synergy here is really extraordinary, I think, for what we can do with those two surveys. So I will stop there and just I'll put my outline back up and take any questions. But just maybe actually right before we finish, just to point out, I didn't mention how deep we are going in the deep and the ultra deep fields. We're going past 28th mag in the ultra deep fields, and potentially, if there are general astrophysics programs that could then focus on one even smaller area, you could go even quite a lot deeper than that, which would be really valuable for the deep, in particular, axis survey. Okay, I'll go and stop there. Thanks.
So I'll ask a question. What is the GEO program going to look like, do you think? Because it surveys like such a wide area. Like, what do you think will be the main like science cases?
So there are a lot of them. Just for some background in terms of what the General Astrophysics Survey program will look like. So 25% of the Roman observing time will be available for general astrophysics surveys. I think that the latest understanding, I think, is over the course of the mission, just to say the number of those that will be supported is relatively limited. So I think it will be a few dozen of those will be supported over the course of the mission, which means if you each one of them will have to be a significant investment in Roman observing time. But there are many different things that one could consider. Just to highlight a few of them that were proposed, things that were proposed in white papers for the high latitude wide area survey that we didn't end up putting in the survey, but we highlighted in the committee report, which, by the way, anybody can look up. It's on the NASA website. There are a few things like doing targeted surveys of a bunch of nearby galaxies to get resolve stellar populations of those. A lot of nearby galaxies will already be in our 5,000 square degrees, but you could do a more complete survey of other ones, for example, to get a detailed survey of that. Other things are you could, for example, observe in the longest wavelength filter, the K-band filter, which was a sort of later on addition to the Roman mission, which is valuable for a whole wide range of applications, both in terms of, measuring stellar masses of galaxies, probing through dust in dusty regions, et cetera. K-band is less sensitive than the other filters, so that's why it wasn't included in the high latitude wide area survey, but one could always go back and observe more of these regions or some other region with the K-band. There's also suggestions of going even wider, doing a really very shallow survey over a very large area, which you'd pay some penalty in terms of slew overheads. Roman is very good and very fast at slewing and settling, but if you're going super shallow, then that becomes a bit of an issue, but that's another possibility. So there are a lot of, just in terms of the extragalactic science, there are a lot of ideas that have been presented for that. I would encourage, I think what the project is asking people to do, if you're interested in this, is they would like the community to come together and collaborate on these projects, because there's only a limited number of them that can be supported. Just to say, the data will be public. One thing I didn't mention is all Roman data will be public right away to the whole community and available on the cloud. So there's not really any benefit to getting a proprietary period. It really is an encouragement to collaborate along the spirit of the way that the core community surveys already have been defined.
Okay, other questions?
Thanks. So for the for the supermassive black hole case, the high Z AGN case, and the wide surveys that we imagine doing, how important is it for it to be contiguous? So I guess one way of asking that is, we haven't discussed much using clustering statistics to characterize our sources, abundance matching, et cetera, but how important is that, versus, for example, building up a wide survey from serendipitous fields?
Yeah. So how important is it that the X-ray observations are?
Yeah, on the
particular?
X-ray side specifically.
It's pretty important. The edge effects are significant. If you think about it, ultimately when you're doing a clustering analysis, what's important is the number of pairs between the objects that you're clustering together.
But I guess the question is, how important will the clustering analysis be for these fields?
Yeah, I mean, I think it depends on which particular science question you want to ask. I love clustering analyses. I think they're great, and they're really you can learn a lot of independent things from them, or at least confirm some independent things that do not depend on a lot of the other assumptions that we make in how we analyze, for example, the SEDs of galaxies to determine stellar masses, et cetera, et cetera. There's a whole wide range of things. One thing I would say clustering analyses with AXIS, especially given AXIS's angular resolution and ability to really nail down the multi-wavelength counterparts is really very powerful. One thing I'd say is that there is for a lot of X-ray clustering analyses, the most powerful way to do them is actually a cross correlation between the AGN and some galaxies in a galaxy field. And if that's the case, actually, the X-ray field being contiguous is not as big of a deal, because what really matters is the selection function of your tracers. And so this is where having a big, continuous, uniform survey that will be possible with Roman, especially in the medium tier where we have lots and lots of spectroscopy as well as imaging and really good photometric redshifts and all that stuff. There, you could imagine any axis pointing anywhere in that 5,000 square degrees, once you build them up over time, could be utilized to do a cross-correlation study that could be really powerful.
All right, thanks.
And the same is true, by the way, the XMM data that already exists there, the Chandra data. And, yeah.
Okay, maybe we'll do one more question and then we'll.
Yeah, thanks for the very nice talk. So a question I have regarding black hole galaxy connections. Right now we're working with the order 1 million galaxies. You talk about going up to like 600 million, which would be great. My question is, do you think more will be different? In other words, one can easily imagine going in and strip mining the 25-year Chandra and XMM archives and ultimately using AXIS and combining them with Roman and Rubin and Euclid and ASCAP and wide field spectrographs and so on. And clearly we'll go do it, obviously, to beat down the numbers, and there might be interesting things there. But my question is, do you really think there'll be something new there qualitatively? And if so, how would you go about finding it?
That's a great question. I think the short answer is I'm not entirely sure. It is true, and just to emphasize that the Chandra and XMM surveys, based on the legacy of 25 years that we've already heard, their archives are a really amazing resource for a lot of this kind of stuff. In particular, I think what we don't necessarily, to me, where potentially the most interesting science is there is pushing to the sort of medium to high redshift regime, where we don't have that many really deep Chandra and XMM exposure. It's just really hard to reach those depths with Chandra and XMM, but you could do with AXIS in a relatively small amount of time. And there you probably would want to do it as some kind of contiguous field. So I think the sort of redshift like 2 to 4 regime, where the black hole mass is building up really rapidly, then the galaxies are forming really rapidly, then I think that's the thing where the individual detections that you would get with AXIS are probably the most interesting place. And we don't really have good clustering measurements right now at those redshifts. The galaxy black hole connections, we're averaging over a lot of properties at those redshifts. So at least to me, that's where the most interesting thing would be.
Okay, great. So let's thank all the speakers. So we're going to have a coffee break and come right back into discussion. So if people have other questions